This is the last and final section, 7.5, and this is on vectors. It's called an algebraic approach to vectors. In this section, so we haven't really had any dealings with vectors at this point in this course, and I'm not sure that you probably have done much with vectors in any other course as well. So this might be very new. The good thing is it's most of it's fairly simple. Some of the application problems might be a little challenging just drawing them out because um, just the lack of experience working with vectors. But just to kick off with some definitions, some basic language. So this says a vector is in standard position when it is placed on a coordinate system so that its tail is located at the origin. So it's going to be basically just work like an angle. So you can put the vector, the tail of it at 0, 0. The tip of the vector corresponds to a point, just like we've done with all the other trig we've done. So this point right here would define basically the direction and the magnitude of the vector. So the magnitude being the length of it would represent the magnitude. So again, we could find the length of the vector using the Pythagorean theorem, a squared plus b squared equals c squared, and we would have the length of that. That would be the magnitude of the vector. And we could actually even represent the direction of it by the angle formed. We could represent this as, the cosine of this angle, say it's called theta, b over the magnitude v. That'd be sine of theta would equal b over, and the cosine of the angle would be a over v. So we could represent this angle as well, which would indicate the direction that the vector is headed. All right, so it talks about to avoid confusion between the point AB. So if you're just referring to just this point right here, then we use normal coordinates parentheses to indicate that you're used to. And the vector, which is the ray extending from the origin to the point. So if we want to represent the vector, which is the ray that starts at 0, 0 and extends to that point, then we have to represent it differently because we just did A, comma B. It would just be referring to the point. So what we do is we name it with these little V-shaped brackets, kind of like a sideways V there. So those brackets indicate vector component form, and we call that component form. This is called the horizontal component, and this is called the vertical component. So we could represent vector v as the components a comma b, so the horizontal component. So at this point were 5, 3, we would call the vector 5, comma 3 in component form. All right, so that's basically what a vector is. So direction and magnitude are going to be important with vectors. How long it is going to represent the magnitude of the vector, and the direction it's headed would also be important. All right, so this is kind of just what I just said. So the magnitude of a vector is its length. So referring to figure 1 back on the previous slide, we could find the magnitude of vector v. So again, it was just, let me see if I can draw this. So remember we had the coordinates, and we had vector v, and this was a, and this was b, and so the coordinates, this point here would be ab. And so if we want to represent the magnitude, and the lines around the v indicate magnitude. So when you see those, it means they're talking about the length of the vector, the magnitude of it. And so we would find the length of v by doing a squared plus b squared. So it would be the square root. C squared would equal a squared plus b squared. And then we would square root. So c, which is the vector length, would be the square root of a squared plus b squared. All right, and that's all that is. All right, so let's look at an example. So this says draw the vector v. So let me sketch a little graph here. In component form is 5, negative 2. So right 5, 1, 2, 3, 4, 5, down 2. There's the coordinate, the point that the vector, where it terminates. So draw the vector in standard position and find its magnitude. So, all right, so that would be, so the magnitude is the length of this vector. So if I'm finding that, I would want to say that's how you represent magnitude. with the lines around it. So the horizontal component of the vector, so the vector v is 5, -2. So again, the length of the vector, the magnitude of this is just going to be the Pythagorean theorem. So you're going to do c squared equals a squared plus b squared. All right, and we have c squared equals 25 plus 4. So c would be the square root of 29. And so that would be my magnitude. So it's nothing, no new math. It's just a little the new language. We're using those same things that we already used, just in the context of a little bit different scenario with vectors. All right, moving on to slide 3. So we want to be able to add vectors together, subtract vectors. When you add two vectors or subtract two vectors, the result, we call it the resultant vector. So it says adding and subtracting vectors written in component form is simply a matter of adding or subtracting the horizontal components and adding or subtracting the vertical components. So the good thing is the process is super easy. The figure below shows the vector sum of vectors u and v. So if you took vector u, which has the component form of u would be, well, I've written here 6, 2. So horizontal component 6, vertical component 2. That determines the direction and the magnitude of vector u. And then vector v, -3, +5. So again, that determines the magnitude and the direction of v. So if you were to add those two vectors together, we would do, so u plus v would equal, let me go ahead and write u is 6, 2, and v is -3, 5. And we would add their horizontal components, so it would be u plus v, 6 plus -3. So I'm literally just adding their horizontal components, and 2 plus 5, sorry, comma, 2 plus 5. And so erase the wrong thing. All right. U plus v then would be the vector 6 plus -3, 3, 2 plus 5, 7. So the vector 3, 7, 3, 7. This vector right here is u plus v. That would be the resultant vector of the combination of u and v. All right, same thing with subtracting. The figure below shows the difference of vectors u and v as the diagram indicates. Subtraction of algebraic vectors can be accomplished by subtracting corresponding components. So it's no different in addition, you just subtracting the horizontal components and then the vertical. So if you take the same two vectors, there's u and v, same ones from up here. When you subtract them, u minus v, we would be taking the vector 6, 2, and we would be subtracting the vector -3, +5. So basically, subtracting, we know, is the same as adding the opposite of the vector, just like it's adding the opposite of the number. So it would be 6, 2, plus the opposite of this vector would be +3, -5. And then since we're now just adding, we could then just combine 6 plus 3 is 9, 2 plus -5 is -3. So the resultant vector should be 9, -3, 9, -3. There it is. So you can see that here's u, and then because I'm adding the opposite of v, so the opposite of v is this vector right here, which is -3, 3, -5. And so when you add the opposite of v and u, then you get the resultant vector that we got. All right, so nothing surprisingly new there as far as the math part goes. Then we have scalar multiplication. So scalar multiplication is when you multiply a vector by a integer, a number. It doesn't have to be a real number, it doesn't be an integer. So to multiply a vector in component form by a scalar, a real number, we multiply each component of the vector by the scalar. So the next figure shows the vector v, which was 2, 3. So the green vector is the original vector 2, 3. So when you multiply that vector by 3, 3 times v means it's 3 times the component form there. So that means you just literally multiply each component by the 3, and so the new vector would result, the resultant would be 6, 9. And you can see that. So literally all I did was triple the length of the magnitude, the magnitude of the original vector. So that's all a scalar does. All right, All right, so we'll just go through a few examples here. So example 2 wants us to take the vectors u and v that are given up here in component form, and we want to add those together and then subtract and multiply each one by a scalar and then subtract. So we start with u plus v. All right, so u plus v is equal to, so let me fill this in. So this is 2, -4. We're going to add that vector and -7, 5. All right, and 2, we have the horizontal components. 2 and -7 is -5. 4 plus -4 plus 5 is 1. And so the resultant vector, if we drew it out, the resultant vector would be -5, 1. Simple enough. On this one, we would take 3 times the vector u, which is 2, -4, minus 4 times the vector -7, this is vector v. All right, so we multiply by a scalar. So multiply by scalar multiplies both the horizontal and the vertical components. So you want to basically triple the horizontal length and the vertical length. So this becomes 6, -12. And I'm going to go ahead and do this just to make it a little easier here. So -4 times -7 would make that +28. -4 times 5 would make that -20. And then I can add the two vectors by just adding their horizontal components and then the vertical. So 6 and 28 is 34. And -12 and -20 is -32. So the resultant vector for that one would be +34, -32. Okay, so component form we've already talked about. So another way to represent a vector algebraically is to express the vector as the sum of a horizontal vector and a vertical vector. Any vector can be written in terms of its horizontal and vertical component vectors, v sub x and v sub y, respectively. To do this, we need to define two special vectors. Unit vectors. So unit vectors, basically, I usually indicates the horizontal vector that's of length 1. So it would end at 1, 0. J typically represents the vertical unit vector of length 1. So we want to remember that I is the horizontal unit vector of length 1. J is the vertical unit vector meaning its length is 1. And so it says we want to write V equals 5. In component form, the vector is 5, 12. We want to write that in terms of I and j. So basically, what we would do is we want to take the horizontal component, which is the I vector, the unit vector, times 5. So we would write this as basically 5i plus, and the unit vector 1 times the vertical component, which is 12. So we would write that as 12j. So multiplying this by 5 and this by 12, and then combining those to make them represent the vector. So the component vector 5, 12 would be written in algebraic form as 5i plus 12j. So it's just a different notation. These mean the same thing. This vector is the same as this vector. 5i plus 12j is the same as that. Okay, slide 7. So let's see, algebraic vectors. So now we're looking at representing more in the AI plus bj form. It says if I is the unit vector from 0, 0 to 1, 0, so that's the unit vector, and j is the unit vector from 0, 0 to 0, 1, then any vector v can be written as, and that's what I just was showing you. So ai plus bj is the same thing as writing the component form ab, where a and b are real numbers. And of course, the magnitude would still be a squared plus b squared. We still use the Pythagorean theorem to find that. All right, so we're just kind of transitioning over into the algebraic form of representing a vector. All right, so this says vector v has its tail at the origin and makes an angle. So let me kind of sketch this out here. So its tail at the origin, which is standard form. and makes an angle of 55 degrees with the positive x-axis. So this is the positive x-axis, so an angle of 55 degrees we'll say is here. That's what they're telling me. So here's this vector. Its magnitude is 15. So the length of this vector, the magnitude is 15. It says write the vector in terms of I and j. So in order to write this in terms of I and j, I need to know, so it's going to be equal to AI plus BJ. But I need to know A and B, and I can specifically find A and B for this particular example because I've got the hypotenuse of this right triangle and I've got this angle, and so I can use a little bit of trig to find the length of, to find out what A and B are, to find those values. So let me do a little trig here. So I know that AA is the adjacent side. I've got the hypotenuse, so I could say the cosine of 55 degrees is equal to A over 15. A representing the length of this vector. And I could say the sine of 55 degrees is equal to B over opposite over hypotenuse over 15. And so then I can multiply both sides by 15 and represent A and B. So I end up with A equal to 15 times the cosine of 55 degrees. I end up with B equal to 15 times the sine of 55 degrees. And so I can now say, I could go ahead and calculate this, I guess. Let me do that. 15 cosine of 55, or I could just leave it like this. It wouldn't really matter. 15 cosine of 55 degrees, so 8.6. So this is A is 8.6, and B is 15 sine of 55. So I've just got to change my function from cosine to sine. 12.3. All right, so we have 8.6i plus 12.3j. And that would be the algebraic form for the vector that had that direction and that magnitude. All right, if V is a vector in standard position and theta is the angle that V makes with a positive x-axis, then the vector component form for V is given by, and this is exactly what we just did. It's just a more generalized form of it. Our magnitude was 15 and our angle was 55, and other than that, it's just the general form. If I go back, if I just let 15 be the magnitude V and the angle theta be 55, I would have the exact same thing. So it's just this is just generalizing exactly what we just did. All right. Let me just kind of sketch out though where that comes from, because remember that that's terrible. This is my magnitude, which was 15 on that last problem. This is my theta, which was 55 in the last problem. This is my AI and BJ. So we know that the vector, we can write the vector as AI plus BJ. We also know that the cosine of theta is equal to A over the magnitude of V. And the sine of theta is equal to B over the magnitude of V. And if I multiply both sides by the magnitude of V, A equals the magnitude of V times the cosine of theta. And B multiplied by the magnitude of V equals the magnitude of V times the sine of theta. All right, and so V equals A, which is, if I just replace A with V cosine of theta, I, and I replace B with V sine theta, then I basically just wrote that. And that's where that comes from. So it's exactly what we did on the previous slide. We did it with a specific angle and a specific magnitude. This is just generalizing that. All right. All right, so this wants us just to do the addition, subtraction, some scalar multiplication. But the only difference is these are in algebraic form and not in component form. But again, nothing unsurprising here, so it kind of would be probably naturally what you would think you would do. And so we're going to add that vector and this vector. And we do that by adding their horizontal components. So 4i plus 3i is 1i, and negative 5j and 7j is plus 2j. So that would be our component, our resultant vector, and that's all there is to it. So nothing tricky there. And then the other one, 3u minus 4v means take the u vector and multiply it by 3, the scalar, and subtract that 4 times the vector v. So only difference, again, what we did previously is these are in algebraic form, not component form. So I'll distribute my scalar out. So 12i minus 15j minus, it's going to be plus 12i minus 28j. And then we combine our horizontal components, which is 24i, and our vertical components, negative 15 and negative 28 is negative 43j. All right, and so again, that's nothing different than you do when you're working with algebraic expressions. So it naturally kind of follows it follows along with your natural tendency, what you're used to doing. Let me read through the problem and we'll kind of look at what's going on, and then we'll try to sketch it out and set it up to be able to solve for what we're trying to find. So we have a kid, 6-year-old, gives us his weight. He weighs 61 pounds. He's sitting on a swing when his sister Susan pulls him and the swing back horizontally through an angle of 35 degrees. So we know the angle at which the swing is pulled back and then stops. So it wants, here's the find the tension in the ropes of the swing and the magnitude of the force exerted by Susan. All right, so we have a swing that is, here's the rope of the swing, and it is being pulled back from the vertical. This angle in here would be 35 degrees. So this is the swing. Kid's sitting on a swing. So the weight of the kid is gravity pulling down. So this vector, vertical vector, would represent, so this would be our weight vector, and it's in a negative direction because it's pulling negative. So this is kind of like our origin right here, our 0, 0. So negative 61 would be the magnitude. All right, and then you have Susan, who's the one who pulled so she's pulling this way. So we'll represent that as our horizontal. I'll call it just H. That vector representing the force at which she is pulling the swing back. All right, so one thing we know is that, little physics, is that when the object is in static equilibrium, so she is pulling it back and she's holding it, she's not pulling any further, she's not letting it go. And I'm going to call this, by the way, T for the tension in the ropes, this vector. So this is the tension. So the rope is providing resistance also. So you have 3 forces acting on this swing. You've got the tension in the rope, you've got the gravity pulling the child's weight, and then you've got the sister pulling the swing back. So those 3 forces, when the swing is in static equilibrium, not moving, then the sum of those 3 forces must be 0. So we know that the magnitude of the T vector plus the H vector plus the weight vector should be equal to 0. Actually, let me just name the vectors and forget so the 3 vectors must have a sum of 0 because the swing is in equilibrium at this point. right, so representing these algebraically. So remember, anything that's horizontal, this would be the horizontal component. So this vector is horizontal, so it has 0 vertical. So we would write this as h equals the magnitude, which would be whatever the length of h is. I, since it's like 0 hi plus 0j. I don't need to write plus 0j. All right, this one is vertical, so if I wanted to express it algebraically, I would express it as 60 negative. We know the magnitude of this one is negative 61, but I would j, since it's vertical. So it would be like 0i minus 61j. So I don't need the 0i. All right, so for this one, I don't really have, so I have basically, I can, let me bring this over here. So I can go ahead and insert negative 61j in for w. And h, I'll just leave that as h I, the magnitude of h, whatever h is times I. And then I need for t, I need to express this vector, the magnitude of this vector. So the magnitude of this vector, let me close the right triangle here. That angle's 35. This angle would have to be 55. And I'll use A and B to represent the horizontal and vertical components of this vector. So over here to the side, let me express the magnitude of t. We know that the cosine of 55 degrees is equal to adjacent A over hypotenuse, which is going to be whatever the length of this, the magnitude of t is. All right, and then the sine of 55 degrees will equal B, the opposite side, over the hypotenuse, which is whatever the magnitude of t is. Now, if I multiply both sides by the magnitude of t, that'll cancel out. I'll have A equals the magnitude of t times the cosine of 55 degrees. And over here, I multiply both sides by the magnitude of t, and I'll get B equals the magnitude of t times the sine of 55 degrees. So now I can express the entire t as AI plus BJ. So the hor is made up of the horizontal and vertical components. So algebraically, AI plus BJ. Put the I there. But A is going to be replaced with t, the magnitude of t cosine of 55. So I could write the vector t as, instead of AI, I'm going to say magnitude of t cosine 55 degrees I plus j, which, or bj, b is going to replace by this, so magnitude of t times the sine of 55 degrees. So this is going to replace my t. I can squeeze all that in here. So I should have given myself some more room here. All right, so let me see if I get that in there. So t cosine 55 plus t sine 55. All right, so I've replaced all of this is my t vector, just written just right to there, algebraically. That's t. And there's h, and there's w. Okay. So just doing a little bit of vector operations here, we know that we can, i's are horizontal components, so we can add our i's together. So let me come in here and change some color here. So this hi and this, I left the I off these. Let me go back and put, I left the I, and this should be j off that. So I was trying to squeeze everything in there really tight. So all right, so I have t cosine 55 degrees. So I'm adding this and the other I plus magnitude of h, and those are all I. Plus, now let me add the j's together. Do this in a different color. So the j's are this one in this one. So I have magnitude of T sine of 55 minus 61 J, and that's all equal to 0. All right, so if the magnitude, so the horizontal component is this and the vertical component is this, and it's equal to 0. So in component form, that would be 0, 0. So basically, I could go back to the T cosine 55 plus H must equal 0. And T sine 55 minus 61 must equal 0. Now this one, I have two variables in it. I can't solve this one yet. If I solve this one first, it only has one variable. I can solve for T, then I can replace T over, I can substitute T over here, and I'll be able to solve for H. So I need to solve this one first. So if I add 61 over, I get the magnitude of T times the sine of 55 equals 61, and then I just need to divide by the sine of 55. So whatever 61 divided by the sine of 55 is, it's going to be my T value. I'm going to clear this. I don't need this anymore, so just get this out of the way. Just to create a little room. All right. And so T is going to equal, so let me go to my calculator now, 61 over the sine of 55, figure out what that is. $74.5 $74.5. All right. It doesn't specify where to round, so I'm just going to leave it there. So that is the force, the tension of the rope. Now that I know T, I can replace T over here. So the tension, 74.5, that's the magnitude of the vector T, times the cosine of 55 degrees, plus H equals 0. So let me compute this. Actually, so this is just going to be the negative. It's going to be negative 74.5 cosine 55. All right, and remember the cosine, well, let's see. All right, I just caught something that I realized I messed up. It's just a minor sign I need to fix. When I did my AI right here, this should have been negative because it is in the negative direction. So that is going to impact my A here. So A, the cosine of 55 would have been negative A over T. So A would be equal to negative. So there should have been a negative in front of this right here, right here, right here. So actually, this is going to end up being positive. All right, so easy fix, but yeah, that was to the left. So 74.5 cosine 55. $42.7. All right, so this describes the magnitude of the force with which the swing is being pulled back by the sister. This explains the magnitude of the vector that represents the tension in the rope. We know the weight, and those were the two that I was asked to find.